Yeah, hi everyone. This is Sitarama Penumetsa, CTO at Candela Technologies, and today I'm going to talk about quality of experience of latency-sensitive applications on home Wi-Fi networks. So the Wi-Fi router that we know of the past looked a lot like this. It has lots of antennas. We normally go buy these kinds of routers from the electronics store like Best Buy. And when we buy these routers, we used to look for is it using the latest standard, what is the maximum speed it can support, and so on. The routers of today, on the other hand, not just about throughput, they are also about coverage, because we now have like 30-40 devices in a typical home that are spread around everywhere, and so we normally deploy mesh networks, and so we require these routers to be looking pretty and match the decor in the house. Now, typically when we still buy the Wi-Fi routers ourselves, we go to the store and we look for things like what is the maximum speed it can support, what kind of coverage we can get, and the maximum number of devices that these routers can support. Now, most of these numbers that we see on the box are theoretical values. Now, when it comes to practically what happens in actual installation and an actual deployment is another completely different thing that happens. And in this presentation, we're going to talk a lot about that. Now, how is a Wi-Fi router of the future going to look like? It is going to look like a lot like something that you would put in a closet. For example, a Wi-Fi in the future is expected to be just like a utility, just like water and electricity. When you go and go to a new apartment or you buy a new home, you don't go and install the water pipes and the HVAC systems. They're already there. In the same way, in many ways, Wi-Fi is expected to be already there, already installed in closets. So there's a good chance that you might not even see the modern Wi-Fi router in your home. Now, the future Wi-Fi router is not about the best throughput. In fact, most of the deployments in the future are expected to be at least one standard behind, because if you're one standard behind, the cost is lower, the reliability is higher, and especially if in situations where the customer is not seeing the Wi-Fi router, they don't really care that much about the standard. And it's not about the looks also, because we have kind of faced that challenge and solved that problem. It's not about ease of use, because that problem has also been solved. Most of the routers that we have, both for enterprise and residential class, are much more easier to use, much more easier to configure. We have zero-touch provisioning and a number of other features. So what is the main thing that is important for the Wi-Fi routers of the future? It's all about end-user quality of experience. So what is the end-user experiencing when they're actually using these routers? This is one of the most important metrics that we need to really look into. So if you take an example of a typical home or a small and medium business where you have a Wi-Fi 7 router, for example, and the Wi-Fi 7 router is expected to, at least in theory, supposed to get you well over 40 gigabits per second physical data rate. Now, if it is a 4x4 MIMO router, it is expected to get over 10 gig physical data rate. Now, but most deployments that you would see, a typical Wi-Fi client would be a 2x2 MIMO client. So right off the bat, even though you put the client very close to the router, you are expecting to get about 4 to 5 gigabits per second throughput. That's your best case scenario. Now, if that same client device is 20 feet away from the router, then already your throughput drops by 50-60%. Now, in this particular case, when we ran the test, at 20 feet away, it dropped to around 700 megabits per second. Now, you add other variables like other devices in a home, then that drops the throughput even further down. In this particular case, when we added a few devices to create co-channel and channel interference, that dropped the throughput down to 400 megabits per second. Now, we would say 400 is still very good throughput. If you're trying to do like YouTube video streaming or like a WhatsApp video call or any other delay sensitive application, that would still be more than enough. But in reality, that's not the case. So if you look at this particular example, we ran the same exact test on the same Intel laptop under ideal conditions with near distance. And in this case, we were streaming a YouTube video. And you can see the video quality is pretty good. But then when it goes 20 feet apart far, even in that case, the video streaming quality seems to be pretty nice. But now if you're adding other clients that are sharing the medium with the router, now we start seeing that the quality of the video has gone down, especially when the video is being streamed under best effort. Even though there is a lot of possible throughput available, the video quality is still taking a hit. Now, the same video streaming, if it's done with voice category, we have seen substantial improvement, right? So what this is saying is that QoS is extremely important for end user quality of experience, even though you're using the latest Wi-Fi 7 router. Now, if you take a look at a modern home or an enterprise, we are expecting to have lots and lots of different types of devices. This is an example of one of our test homes that we have in the work that we do. This home has 200 plus IoT devices. The interesting fact here is about 70% of these devices are 2.4 gigahertz only. Now, we have deployed the Wi-Fi 7 router. It supports 2.4, 5 and 6 gigahertz bands, but 70% of the devices are 2.4 gigahertz only. So which means that we need to solve the 2.4 gigahertz problem. So if you look at 2.4 gigahertz, the limitation of course is that we have limited spectrum and we have limited non-overlapping channels, and medium utilization is a huge problem. So if you take an example of an ideal client in the 2.4 gigahertz, like an Intel B200 laptop, in this case we used 2.4 gigahertz with 20 megahertz channel bandwidth. So the theoretical throughput is around 275 Mbps under ideal conditions. So when we ran some tests using this model, when we load the channel by about 30%, we are getting good theoretical throughput as a percentage of theoretical throughput, and we are getting channel utilization that is comparable. So for example, when you are hitting about 36% of theoretical throughput, we were using 55% of the medium. And as we get closer to 100% of the theoretical throughput, we are using most of the medium. And this is happening very well because the Intel client is using the maximum possible phi rate. It is also doing the largest aggregates. So it tends to use the medium very efficiently. So we are seeing good efficient medium utilization with this device. But again, in a typical home, we would not just see a bunch of laptops that have Intel clients. We will have IoT devices, smartphones, tablets, laptops. We have doorbells, we have surveillance cameras and so on. And again, majority of these devices, like in this lab that we set up for this particular test, we have a lot of these IoT devices. And when we actually try to characterize the medium utilization of these devices, we find very interesting results. So let's say you take like a surveillance camera or a HomePod or a Alexa. When we run application traffic with these devices, the amount of throughput they need is actually very low. If you can see an example of an Alexa, it's only taking about 2.5% of the theoretical throughput when we run an application on it. But for that 2.5% theoretical throughput, it's actually taking about 26% of the medium utilization, right? So the medium utilization is proportionately higher when compared to the throughput, and this is happening because these devices are transmitting at very low phi rates and are also not aggregating, and they potentially have a lot more retries, and they're also using a lot of other control management frames for their communication. So they're taking up a lot more medium time even for lesser amount of throughput. Now if you have about 5 or 10 such devices, you're taking up already 70-80% of the medium, which causes other delay sensitive applications to probably not work very well in the 2.4 gigahertz band. So how does this result in if you actually run a real test with a WhatsApp video call, for example, in the 2.4 gigahertz band? So if you run a WhatsApp video call under again ideal conditions when we don't have any interference, the call is going well and we are without any congestion, we are getting good quality. But if we add these 4 or 5 IoT devices into the mix, you can see that the quality is taking a big hit, and you can see the video is stalling, the WhatsApp video call, the user experience is really bad unless we implement some form of QoS mechanism. Now this is still, remember that this is the latest Wi-Fi 7 router that we're using, but still it has basic performance issues when it comes to video quality. Now how do we solve this problem? Of course there are many ways we have been trying to solve the problem. Of course one of the simplest, most common method is to do better QoS tagging. That generally works in most cases. There are other, of course, methods like using multiple radios. You can have a dedicated radio or multiple dedicated radios for 2.4 gigahertz band, but that's not going to solve the problem that there is still limited bandwidth in the 2.4 gigahertz band. We can use better band steering algorithms, so we can actually make sure that any device that supports 5 gigahertz is moved to the 5 gigahertz band, and so that for 2.4 gigahertz is only left for the devices that only support 2.4 gigahertz band, and certainly we can implement better band steering algorithms. Of course, there are modern techniques like OFDMA and multi-user MIMO that can do a better allocation of spectrum and improve spectral efficiency. But again, for these methods to work, the devices also have to support those features, which is highly unlikely with these IoT devices. Now, of course, again, we can use other techniques like multi-link operation, that is part of Wi-Fi 7. Again, we have the same problem. These IoT devices are not most likely going to implement those methods. And then we also have Wi-Fi HaLow, which is a very promising future technology where we actually can deploy these IoT devices in sub-gigahertz frequencies, and we can use smaller frequency chunks like 5 megahertz and so on, where that is more than enough for these IoT devices to operate. And we can have future access points that have HaLow radios that move all the IoT devices to sub 1 gigahertz, and then you can still use 2.4, 5, 6 gigahertz for your normal transmission, which can be very, very efficient. Now, till most of these methods are implemented, it is still very important to test your Wi-Fi router under these kinds of test conditions. It's not enough to just measure throughput under ideal conditions, because that's not the problem that a typical Wi-Fi user is facing. We have to subject the Wi-Fi router to realistic test conditions, and we have to use, as an example here, we have this home in a box solution where we try to create this scenario where we try to bring the entire home environment into a box using a combination of RF enclosures. We can create some near clients, medium distance clients, far clients, clients that are using different protocols, different specs, different types of data rates, and they're all trying to run different applications. And now we are subjecting these routers to a combination of mix of different types of load patterns, and now we are trying to see how well the applications are working under all these kinds of ideal conditions. So this kind of testing is extremely valuable and important, and while throughput is a very important factor, end user quality of experience can only be tested when you actually subject the Wi-Fi router to all these different types of conditions. So I hope you found this session useful. Thank you for the time.